не туда.
Мне кажется, неправильная камера.
Ну, по крайней мере, половина видно.
А, нужно все, да, точно, я забыл, что мы посмотрим. Так, вроде все видно.
Ну, почти. Вот, ну, так точно все, но там кусочек еще вес.
Можно
чуть-чуть увеличить.
на один.
Так. Ну вот да, да. Микрофон отлично. Все, это здесь все управлять.
Да,
плюс-минус без.
Должна пойти. Ну, надеюсь.
Okay, so just briefly remind what we were doing last time, because I want to finish this. So we're proving the theorem, the exchange theorem. So in that theorem we consider, so let me draw the diagram. So this is a standard diagram that I'm going to use many times today. So that's kind of the base change diagram. So this is a pullback of Cartesian square. So the maps are called F, U, prime, U prime. So let this be this diagram be a Cartesian diagram. Of quasi-separated schemes. And this diagram maps F and U are quasi-compact, quasi-separated. Then the following following three conditions I call them. So the first condition is that the base change map is an isomorphism, so the base change are called theta. That's the map from the pullback by U composition to the push forward by F. So to the push forward by the F prime composition with the pullback by U prime. So this is an isomorphism of functors. So the second condition was the unit map. I called this map eta, which was the map from the tensor product of the push forward along U of some object E. So tensor product, the push forward along F of some object F. So there is a kind of canonical map that we constructed last time. To the push forward along the G. Remember that G is composition of any of these two maps. So push forward of the tensor product of the two pullbacks. So pullback.
Yes, E prime should be upper star, not lower star.
Here, right? Yeah, okay. So here take a tensor product of the pullback by F prime over E. Tensor product with the pullback along the U prime of F. So this map that also is an isomorphism. And finally, the last condition 3 is that the maps F and U are Taurian dependent. So F and U Taurian dependent over S. Sometimes also people say that the schemes S prime and X are Taurian dependent over S. So we proved almost everything. We proved two implications. So the one that 1 implies 2 was quite easy. The 3 implies 1 we proved last time. So what's left is to show that 2 implies 3. So again, this will be some work. I separate this into the 3 steps. And the first step I want to leave as an exercise, this kind of tedious check of some diagram lemma. So in this step 1, I said that the given a diagram, which is kind of the composition of two pullbacks. So u prime over s prime, x prime. So this is the new piece. And then there is the diagram as before. Yeah, so this is f prime, this is u prime, and I also need map v. So probably I don't need any other maps in the book, so I don't want to give them names. So, but I want to give the names to the squares that I have on this diagram. So I have squares 1 and 2. So we know by assumption that, as usual, 2 is Cartesian. This is also Cartesian, since I wrote this as a fiber product. So by the general categorical property, the rectangle is a pullback of fiber product. So everything is Cartesian here. So the claim is, so given a diagram like this, if the unit map for 1 and 2 is an isomorphism, then it is an isomorphism. It is an isomorphism for the rectangle. So I don't want to prove this. It's kind of straightforward, but not very short. So I'm going to leave this as an exercise. There will be one more diagram of this kind later. Well, one more, sorry, lemma of this kind. Okay, so step 2 of the proof. In this step 2, I want to show that if the map V, like on this first square, so if V is an open immersion, so then the unit map of 1 is an isomorphism. Right, so this is what we need to show. So as the assumption is that we have 2, right? So we know that it is given that for this diagram the unit map is an isomorphism. We're going to check by straightforward computation that this is an isomorphism for diagram 1. So this then will be the isomorphism for the rectangle. So we already know by the lemma that we proved a week ago that for open immersion, I don't want to repeat the condition, but the fact that this open immersion implies, first of all, that the push forward by this map V is conservative functor. So that's something that we know. And also there was a remark when we proved very first implication, so the implication that that 1 implies 2, we saw that if the functor is conservative, that 1 and 2 are equivalent. So 1 is equivalent to 2 in this situation. Right, so instead of proving that the unit map is an isomorphism, I can show that the base change map is an isomorphism, and that is very easy. So the base change, so let me write the base change in this case. So since this V is just an inclusion of open subset, I'm going to write it like this. So they push forward along. No, actually I need a name for this map, so let me call this F double prime. So they push forward along F prime of the some object f, then I restrict everything to the u. So this is isomorphic to the push forward along f double prime of the f restricted to the, well, I think the formula is short if I just write f prime inverse of the u prime. Right, so this base change map is the isomorphism. And to check this, we just take a k-injective resolution. So indeed, let's choose a k-injective resolution from the f to the, so this is quasi-isomorphism from f to the e. This is k-injective resolution. And then, again, you can verify this as a very simple exercise, that whenever you take a k-injective object, you restrict this k-injective object, so in this case by the f prime inverse of the u prime. But in general statement would be you take a k-injective object, you restrict this to an open subset, this is still k-injective. So here's k-injective. And so then you just can do this computation, reduce everything to this, well, you write the derived functor for the push forward along the f prime of the f restricted to the u prime. So this you can write as the f lower star with a prime applied to the k-injective resolution, then you restrict this to the u prime. So then by the underived version, this is f double prime push forward of the resolution I restricted to the f prime inverse of the u prime. And again, by this remark that the restriction is still k-injective, so this will be a resolution of the f restricted to this subset. So I can write this as the derived functor of the push forward of the f double prime of the f restricted to this thing.
What is u prime? What is u prime? Is this?
So that's a kind of open subset in the S prime.
Yes. And what is u?
There is no u.
So everywhere where you use u, it's u prime.
Yeah. So is it somewhere else? I think the rest are just u prime. Okay. So that's the argument for this step 2. And finally, the actual proof. Which is kind of long, but I think very easy. So in the step 3, I finally want to show that the u and v are Tor independent, right? So I proved that if I have a unit formula, I can kind of restrict, take an open subset in the S and restrict, kind of do this base change by the open inclusion and restrict to the case where this is kind of the open inclusion, right? So instead of considering the general S prime, I can consider just an affine open subset here, and the unit formula is still correct, right? By what we have by step 1 and step 2. But of course, the argument is symmetric. I can as well choose an affine open in the X, right? But the being Tor independent is a local property, so it's actually enough to check this for kind of every affine open. So let me say that since the diagram, well, that this main diagram that I have in the statement of the theorem is symmetric, so we can pass through the subsets of X and F. So for S is kind of the step 1 and step 2. For X, by the fact that this is symmetric. So I want to assume that the S in my diagram now is spec of some ring A. S prime is, so everything is affine. So S prime is the spec of the A prime, X is the spec of B, and finally X prime is the, so that's the base change, so this is the spec of the tensor product. So I have some mistakes in my notes. So X is B, so B is an algebra over A, right? So this will be, I think, A prime and A, and this is B, right? Checkmate. I think I have some different notation in my notes, and I think my notation in my notes doesn't work, so I need to kind of work out this at the moment. Okay. Okay, so now in this case, when we do everything for the kind of the affine situation, of course the map U that left in the diagram is an affine map, so then the functor R U log star is conservative as before, and 1 is equivalent to 2, right? So you let me write this, U is affine in the affine situation. So condition 1 is equivalent to condition 2 as before. And
Who is U?
Hmm?
Who is U? You mean
Well,
S
I'm-
prime, yeah?
no, I'm still thinking about this diagram, but now I assume that in this diagram everything is affine, so I still use notation U for the diagram.
Ah, U small, okay, yeah.
Yeah, small u, yes. Okay, so current formula is equivalent to the base change, so, and I want to just take a base change isomorphism for object which is the structure shift of the X. So theta, so the component for the structure shift. So this will be from the pullback by U composition with the push forward by F of the OX. That's an isomorphism with the push forward by F prime composition with the pullback by U of X. So this is an isomorphism. Right. But now I just want to take this isomorphism and rewrite this in terms of these algebras.
Yes, the last one should be LU prime upper star. Not to confuse anyone.
Where?
The last part of the isomorphism, yeah,
Here?
U prime.
Yeah. Okay. Okay. So we have this isomorphism, and now let's write the left-hand side in terms of algebras. So the pullback of the U prime push forward by the F of the OX. Right? So I want to write that this is something to which I apply the tilde, the associated shift that associated to the module. Right? So here I'll have, so this push forward is just a tensor product. So I think this is A prime A and B.
Why?
Is it right? The right product. Well, so let's check this. So I have this OX, right? And I take the push forward, which just means that I consider B.
OX is B.
Yeah, so I consider B as an A module. So then I take the pullback, right? And the pullback, if you're in a fine situation, that's just a tensor product. So that's a tensor product. So since u is from the S prime to the S, tensor product with the A prime. Okay. So that's the left hand side, and now for the right hand side. So push forward by the F prime composition with the pullback U prime, and this is applied to the OX. Well, first observation that I can drop the derived factors R and L. So I can write this as the F lower star prime, U upper star prime applied to the OX. Right? Why I can do this for the L, for example? Well, that is because OX is a flat object. Okay, so therefore on the Z object I don't need to derive it. And now for
Prime because it's affine.
yeah, because everything is affine, so I don't need to derive F prime. Yeah, so that's the first observation. Now, for the second observation,
Why you didn't derive U prime?
because OX is flat.
Yeah.
So now I'm using again for the structure shift the underived base change that I also used last time. So this will be the U upper star, so pullback with the U, composition with the push forward by the F, applied to the OX. But this is now, since everything is underived, I can write this kind of as the same formula. So this is A prime tensor product over A with the B, but this is not tilde, but this is not derived. Right? So I'm saying that essentially I'm done with the proof, right? So I see that whenever I choose an open affine subsets, I'll get that the derived tensor product is the same as the underived, which means exactly that all the higher Tors are vanishing. And that's the condition, one of the conditions for the Tor independence. So maybe just to combine everything together, write this as a formula. So one tensor product is derived, one is underived, and which means that the higher Tors starting with one is more vanishing. Okay, so that's the end of the proof of the base change and the end of this chapter 6. So finally, I want to start chapter 7, which is chapter on duality. So this is. So you can see that it's almost impossible to immediately start with Grothendieck duality. You need a lot of the preliminary work on triangulate categories and algebraic geometry. So first section, I'm going to call this as a statement. So the derived category dx, so remember this is all complexes of OX modules with quasi-coherent cohomology. So this category is compactly generated. Right, so why this is a kind of natural first step? Well, because in this case, if this is compactly generated, well, of course, this for some assumptions on the schemes, but if that is the case, well, you have the push forward, right, the derived push forward. We already know that this derived push forward commutes with coproducts. Hence, by the Brown's representability theorem, there is a right adjoint. That's the right adjoint, which is the functor that we can see in the Grothendieck duality, for example, for the proper maps. Okay. But first I need to show that this is a compactly generated category. First lemma is the following. So let X be a quasi-compact, quasi-separated scheme. So then I have the inclusion that the perfect complexes on X are all compact objects in the derived category. So in fact, for the quasi-compact, quasi-separated, these two subcategories coincide. we already know this in the affine case. I think that was an exercise at some point. But this is true for any quasi-compact, quasi-separated scheme.
So,
And
do you know it goes in another direction?
no, it will follow from the compact generateness very easily, but we need to prove this. And in the proof, we need this lemma. So it's kind of separated into two steps. One inclusion will be straightforward, and another follows from the main theorem. Okay, well, the proof of the lemma, I think, is also not very hard because, well, if you take a perfect object on the x, right? So let's call this E. Well, the first observation is that, so what I need to show, that this is a compact, right? So I need to check that if I apply home from the E to the coproduct, I can kind of pull out this coproduct. So clearly I can do this if I work with the local homes. So let's call the coproduct of objects, so objects in the coproduct AI. So I have this formula. Do you see why this is a correct formula when E is perfect?
Homicide?
Hmm?
Because of homicide? Probably.
Or what?
Because of the problem for Unix. That wasn't homicide.
No. Because one of the theorems that we proved before, we proved that when the first argument in the home is perfect, then this home is actually
Not derived.
no, it would be derived, but this is quasi-isomorphic to the tensor product, derived tensor product of the E and the second argument.
Mm-hmm.
And for the tensor products, this is well-known statement. Okay. So this is true for the local homes. And now to go to the global homes, well, I just have the following observation. So suppose I have now another object, so say for object B, which is just now any object in the derived category. So we have home from the E to the B. Now this is kind of the global home, the home in the derived category. Well, first of all, I can write this as the zeroth cohomology of the R home from E to the B. Right, so this is non-local R home. Also, I can rewrite this and write this as the H0, still the same H0, but for the R home, since I know that the global home is the composition of the functor gamma and the local home and the composition of derived functors, derived functor of the composition is composition of derived functors, I can write this as the R gamma composition with the R local home from E to the B. Okay, well, and whenever you kind of compute the R gamma and then compute the H0, so you can as well write this as H0 x R home E. Okay, so that's kind of as a reminder and the identity that I'm going to use in the proof. So then if I compute now the global home from the perfect object E to some direct sum of the AI, well, I can write this as the H0 x R home local from the E to the direct sum of the AI. Now for the local, I can pull out the direct sum. This will be R local home EAI, right? And then finally, I can also pull out this direct sum from the second argument in the first cohomology. So this is direct sum of the H0 x R home local E which is, of course, finally we can write so the same direct sum, but just as global home from E to the AI. So the last one is by this observation with the B before. And the question is, maybe the only non-trivial step here is why I can commute this direct sum with the cohomology. Well, before we, actually, because we proved a more general statement, we proved that they push forward, if the map is quasi-compact, quasi-coherent, the push forward commutes with direct sums. And now this is just a push forward to the point, and the scheme is quasi-compact, quasi-compact, quasi-separated. Hence, the map to the point has the same properties. Yeah? Okay. So that's the proof of this lemma. Okay. Now to prove the statement that I want to prove in this section that everything is compactly generated. This of course by induction, right, by the number of the affines, open affines that you need to cover X. The base of the induction is already known, but to do the step of the induction, I actually need some kind of more or less standard commutative algebra. So let me do some piece on commutative algebra. So let B be a step of some commutative ring R. I assume that I have several elements, some sequence of elements, which is not necessarily a regular sequence. Then this sequence defines, maybe let me also introduce notation, maybe it will be useful for the ideal generated by this sequence. And the closed subscheme Z will be just the V of this ideal, some closed subscheme. And this closed subscheme has an open complement. So U, which is the open complement, so this is V minus Z. Or in other words, this is also the union of the principal open subsets of Fi, so the union between 1 and 5. And this U is also can be embedded into the V, and I'm going to call this map J, so the open embedding. Okay, so that's, yeah, and finally, also, I want to consider the Koszul complex. So, Koszul complex. I'm going to call this K for the shortness, but this is the Koszul complex for this sequence of the elements in the ring. Okay. So lemma from commutative algebra. So let E be complex of object in the DV. So that's just the complex of the R modules. So then the natural map, which you obtain as just the unit of the adjunction, so from U to the derived push forward composition with a pullback. Well, pullback is exact, so we don't need to derive it. So this natural map is an isomorphism. It's an isomorphism if and only if home from K shifted by N to the E is equal to 0. So this is of course home, which I take into category D of V. So this is 0 for any integer N. So another way to think about this lemma is to remember that in the assignment 3 there was a question about the derived category with I torsion cohomology. Right? So another way, geometrically, you can say that you consider subcategory here such that all cohomology of the objects are supported in a closed subscheme, and this subscheme is given by some ideal like that because in this assignment the ring was not linear. So So essentially this statement is the statement that in this, there was a question, is that category compactly generated? So it's compactly generated and the Koszul complex is a compact generator. So essentially that's the answer to that question from the assignment 3. So there might be different proof for this statement, but here I want to notice one simple thing, that condition that the home from the shift of the Koszul complex to the E is equal to 0 for any n. This is equivalent to saying that the R home KE is equal to 0. Now there is no n, right? And why this is the case? Well, because a simple explanation, if you look at the home from the Koszul complex shifted by n to the E, well, you can identify this with the x, with the index minus n from k to the E, right? Right, and since this is for any n, all the x are 0, but this is the same as saying that R home is quasi-isomorphic to 0.
Isn't this R home should be not sheaf but a middle so strict H?
Here?
Yeah.
Yeah, sorry, yeah, this is the global complex.
Global.
Okay, so this is if and only if statement, so let's go in one direction. So let's assume that the home, well, as under this, rewriting this, we can assume that our home k and E is equal to the 0. So I want to consider a special case and then reduce everything to the special case. So consider first the case where you take this pullback along the map G, which is an open inclusion of the E, and assume that this is 0. So in other words, homology of the E supported on Z. Or you can say algebraically that the homology of the complex of our modules are I torsion. So then I can, with this given condition with the R home, I can rewrite this. Right, so 0, which is the R home from K to the E. Since Koszul complex is perfect complex, I can write this as the K dual tensor product. Well, I don't need to derive tensor product again because this K is definitely K flat. It's finite complex of 3 modules, so it's finite complex of flat modules. So tensor product with the E. And also by commutative algebra simple argument, you know that if you take the dual of the Koszul complex, you still get the Koszul complex but shifted. So this will be isomorphic to the K shifted by minus R tensor product with the E. So saying that the home from the Koszul complex to the E is 0 is the same as saying that the tensor product, right? And since I can definitely shift this back by R, this minus R doesn't play any role in the computation. So, yeah. Assume that the K tensor product with E is quasi-isomorphic to 0. Now, for this, even for this special case, I want to consider special case that the R is equal to 1. So there is only one F. Okay, so in this case, since I still have the assumption that the pullback of the E is 0, so maybe we can squeeze it here. So the pullback of the E in this case is just the E restricted to the principal open subset given by the F, and that is 0. And also the second condition about the tensor product with the Koszul complex, well, this just means that you have very simple complex, so the Koszul complex for one element is just this is a simple complex with two terms. So then the product with E is equal to 0. Or is isomorphic to 0, so 0 in the derived category. But how we can compute the cohomology of this tensor product? Right, so we can just take the corresponding spectral sequence. Right, so for example, we have something like H1 of the E. This is multiplication on F1, H1 of the E, so it's continuous for any index. So then there will be H0 of the E, F1, H0, etc. Right, so I'm using spectral sequence to compute the cohomology of the tensor product. I compute the cohomology in this direction, and there are induced maps on the cohomology, which are multiplications on F. Right, but we know that the spectral sequence converges to 0, and that's only possible if the multiplication on the F1 on Hi of E is 0. Sorry, is isomorphism, sorry. To get the 0 cohomology, this has to be an isomorphism. Right? But we know by this condition that the cohomology, all the cohomology that we have here are I-torsion. So it means that this F has to be nilpotent. So I take an element here, right? So on one hand, this F, multiplication F, is isomorphism. On the other hand, this is a nilpotent operator. So this is only possible, it's an isomorphism, and Hi of E is I-torsion. So this is an isomorphism and also nilpotent if this is only possible that the cohomology are 0. So Hi of E is 0 for any I. Okay, so that's the proof for the kind of special case of the special case. If I assume this, and then I assume that I have only one element, then I know that I have the proof that, well, actually I know in this case,
may I ask, do we know that Hi of E is finite model?
no,
So why we know that it's E, is that F is nilpotent?
well, it's nilpotent for any element. You can take any element, say in the Hi
Yes.
of the E, and since this is I-torsion on this element, you're supposed to have some power such that Fi to that power, F1 to that power is multiplied by M is 0.
Yes.
But we also know that multiplication on F1 is an isomorphism.
Yeah, so multiplication on F could be not nilpotent, but this what you say is true. So it's not nilpotent, since if it's nilpotent, it's for all elements should be at once 0.
That would be true if the cohomology finally generated.
Yes, but cohomology not finally generated. So
They're not finally generated, but you still have the property that I said,
yeah, you have
nilpotence.
the property, but multiplication on F is not nilpotent.
Well,
That's another.
Just in here.
Sorry?
Yeah, but it's not nilpotent. It's not.
okay, locally nilpotent. Okay. So what I want to say that in this situation the cohomology of E is 0, and of course clearly for the 0 object that's an isomorphism, so it's kind of proof in one direction for special case to special case. Now let's do a little bit more general situation. So let me assume that I actually have a complex, Koszul complex for several elements, and remember that I can take the Koszul complex and write this as a tensor product of Koszul complexes for one element. Right? Again, just one of the standard properties of the Koszul complex from the commutative algebra, which you can easily verify. Okay, so then
I want to use the induction. So this is a general case and use induction now on R. Let me write J sub R to be the following composition. So this will be UR. So this is just by definition the principal open subset for the FR. And this is embedded, of course, in the U. And I want to call this embedding JR prime. And then there is kind of the general embedding of J of the U into the X. So consider the composition of these two maps. Now, if I take the pullback along the JR of the tensor product, say of the K, now I have the Koszul complex but for all elements but the last one, so up to FR minus 1 tensor product with E, right? So then, well, clearly this is 0, right? Because, well, I can write this as a pullback applied to the Koszul complex. And then tensor product with the pullback applied to the E, right? But this term, this pullback is 0, right? Well, because I can look at this pullback as the composition of the two pullbacks, and what?
Then J upper star of E is 0.
J upper star
Of E is 0. This is the case that what we can see now.
Ah, yeah, so that I was confused too. So by the assumption that we have this, so this pullback is 0, hence this whole pullback along the JR is also 0. So this is 0. So first of all, this is 0, and yeah, and then the second simple observation is that when I write the tensor product of the Koszul complex with the E, I can write this as the tensor product of the Koszul complex with K of the FR, tensor product with the Koszul complex for all other elements except the last one, tensor product with E, right? And my assumption is, of course, that this is 0, right? But now, since I know the case of one element, now in this case, this will be the element FR, right? I can conclude that the tensor product of the K of the F1 FR minus 1 tensor product with E, this is 0.
Yep.
So this is by the case of one element. And then this is kind of the proof of the induction, right? If I know the statement for the all elements, I know the statement for the R minus 1 element, so that's the step in the induction procedure. So by the induction, we know that this now works for this special case, right? So finally I want to remove this assumption that we have this special case. And to do this, I look at the exact triangle. So how about I just erase what's on this whiteboard?
How calculate the tensor product of the last tensor product is 0?
This one?
No,
This one?
Yes.
Well, by the case of, I look at this object, right? It's kind of new object E prime, this tensor product. So I notice that it has the property, if I take the pullback of this object, this is 0. And I also have the property that if I have a tensor product with Koszul complex with one element, I still get 0. So this is 0 by this computation with one element.
Yeah.
Okay, so I want to kind of write the rest of the proof here. So I have the assumption on the E, and I want to remove this assumption. And this is done again by looking at the, so let me say that apply the functor R home from the K to distinguished triangle, which is distinguished triangle that we used before. So the local cohomology distinguished triangle. So that's a distinguished triangle. And about this distinguished triangle, I can notice several things. So note.
So for E upper sheet, isn't it L should be? It's then should L to
No.
left to right.
No, this is right.
Yeah. Okay. So,
Yeah, and notice that kind of the whole idea of the Grothendieck duality is to develop this F upper Schrick functors, right? And here I already use it, but note that this is a distinguished triangle in the OX modules. It's not a distinguished triangle in the, and this exists automatically by some topological properties. It's kind of statement from the topology. Okay, so about this distinguished triangle, so the argument is very easy, but I'm always confused how the argument goes. So I want to note several things. First of all, that if I apply the J upper star to the I lower star R I factorial E upper Schrick, right? So then this is 0. Right, so this is 0 because I have the embedding I lower star, so this whole thing is supported on the set Z. So when I restrict this to the open complement, I'll get 0. So this means that this object in this distinguished triangle is the object for which we know this property. Right, so then this is the first thing that we can note. And the second thing that we can note is the following. When I compute home, or R home, so sorry, I think what I don't want R home. I want to apply home as the cohomological functor. Just look at the log exact sequence. I think that's enough. Okay, so when I look at the home from K to the last term, so push forward, go back. Sorry, this is F somehow. This is not F. This is J. So this is J, and of course this is J. Right. So this is applied to the E. Well, I can do the adjunction. I can write this as the home pullback of the Koszul complex pullback of the E, but that's 0, right? Because the pullback of the Koszul complex is 0. Again, Koszul complex has cohomology supported on the Z. So when I restrict this to the open complement, that's a object with 0 cohomology. Okay, so this one will be 0, and when I apply the home K, right, so since the terms here home to this thing will be 0, what's left is just the identity, or maybe I want R home, sorry, but it still works, right? So the adjunction works also for the derived functors, right? So what I want to say that the R home from the K to the I lower star derived function of the I upper star upper Schrick of the E. Now this will be isomorphic to the R home from the K to the E, right? Which is 0 by our assumption, right? We assume in this case that R home from the K to the E is 0. So then we have that R home from the K to this first vertex in the triangle is also 0. And yeah, and since we know the special case, since we know that this object that we have here, right, is satisfying the special assumption, and by that argument that we have before, we prove that this is 0. So the conclusion is that the I lower star I upper shriek E is isomorphic to 0. Which is what we want, right? Because if this object is 0, then this map that I have in the lemma, which is precisely this map, is an isomorphism.
So when we need the whole computation for R home from K to E, since if we have the J upper star of this E lower star R upper shriek I upper shriek E is equal to 0, so is after node.
Yeah, so
Yeah,
this
we have
is.
it. And then we have the case, so from it. Yeah.
So I also want this condition that R home from K to this object is 0.
Yes.
And this I get from the distinguished triangle by applying R home and noticing that something is vanishing, namely this term when I apply home is vanishing.
Mm-hmm.
So then I get this isomorphism. This is 0 because it's given to me. So finally I have the R home from K to this object is 0, and that's the object that satisfies this condition of the special case.
Yes.
So that's the proof in one direction. And the proof in the other direction is actually quite trivial, right? Because if this is just the same argument that I just used, right? So if I look at the R home from K to the E, right? So I know that this is an isomorphism, and I want to show that the R home is vanishing, right? But I can rewrite this by my assumption, right? By the assumption I can replace E by this thing. So this will be R home K R J lower star J upper star E, right? But this is the same term that we have here, which is by adjunction is equal to this term, and the pullback by J of the K is equal to 0. So this is 0 by the same argument as before. Okay, the end of the proof.
Mm-hmm.
Can you repeat the argument, please?
So in the other direction, I know that this is an isomorphism, right? So and I want to show that this is 0. So I replace this E by this object, since it's isomorphic, right? But for this object, this is the home that I have here, and by the adjunction, this is this home.
Yes.
And then this home is 0 because this is pulled back to the open complement of the Koszul complex, which has cohomology on the closed subset. Okay. Okay, so then I want to notice several things. I don't want to kind of write this as a statement, but let me use the assumptions as before. Let me also introduce notation that the d of x sub z, this will be just by definition all the objects in the category d of x, such that, well, I can say that the support of the object is in z, or equivalently, I can say, so equivalent way to define this subcategory will be by saying that if I restrict this to the open complement, the assumptions is as before, well, except maybe that I switch v to the x. X is the same as, sorry, maybe I shouldn't have used this v to begin with. So this is
What's
the
difference from this category and categories that we have in assignment 3, dxi?
it's the same thing.
Okay.
But in the assignment there was a special case of an Arthurian ring, so this is kind of general ring. There I just only assume that I choose the ideal which is finally generated.
Isn't that all we needed for this assignment? Or is there?
I
No, I suppose for, yeah, suppose we need another.
No, theorem condition simplifies several things.
Yeah.
Okay, so just reformulating this condition, I can as well say that the pullback to the open U is quasi-isomorphic to 0. That's the same category. And observation that I could have in this affine case and actually could be generalized to the non-affine case is the following: that the derived category of the U, well, this is not affine scheme. This you can identify by the Thomason kind of, well, not by the, well, you can identify this with the d of x quotient by the subcategory of the d of x z. So, and this is an example of the Thomason localization. So, example. Thomason's localization. Okay, but to know that this Thomason localization, well, since, well, we already know this is compactly generated, right? So it's in this affine situation. For affine situation, we know that derived category is compactly generated. You only need to realize that this subcategory dx sub z is log of some compact set of compact objects. So let's do this. And I claim that this set of compact objects is, of course, the Koszul complex, right? So clearly, the K is the compact object, right? And moreover, this is clearly a compact object in the dx sub z.
Yeah, from where we know that d of u is isomorphic to it?
Well, this we know, I think, just by the general algebraic geometry, because you get the corresponding statement for the affine. For the abelian situation. You get that you can present the quasi-coherent shifts on U as the quotient of quasi-coherent shifts on X, modulo quasi-coherent shifts on X supported on Z. And then you can...
This for abelian case.
Yeah.
And why it's the same in derived?
Well, you just kind of take the same functors, you derive the functors, and you check that everything works.
Okay.
So that's the general property. That's not for affine case, and for the general case, for any open subscheme, you have the following: that you have quasi-coh on X, and this is mapped to the quasi-coh on U. Well, it's kind of standard exercise in algebraic geometry to show that this is essentially surjective. And then there will be some kernel which is quasi-coh on the X, but supported on the Z. Right. And then you kind of check that when you go to the derived categories, everything works. But this is not very hard. It's relatively straightforward since you know that all the functors that you have. Well, for example, you have here this will be just the restriction, then the adjoint will be the kind of the push forward, right? So we have this identity. Composition is identity. For the derived versions also identity. Well, it's kind of standard way with the derived functors. Nothing really interesting happens when you derive this version, derive this exact sequence of abelian categories. Okay, but I just trying to explain at the moment that if I take the log of the Koszul complex, I'll get exactly this. So that's the goal. So, yeah. So first of all, if you just apply one of the theorems of the Thomason localization, we can notice the following: that if I take the log in the derived category dx sub z of the K, right? So this is the perfect complex, so it's a compact object. And then this thing is the whole derived category d of x sub z.
Do we know the d of x sub z compactly generated?
No, not at the moment, no.
So how we can use that?
This statement here, right? This is just a way to state this lemma. Well, because what you have, if you take an object here, right? So that's an object E exactly with this condition.
Yes.
So, and we saw that if you have home from the K with all the shifts is 0, then this object is actually 0.
Yes, so it's Gx of Z is compactly generated by K.
Yeah, so it's compactly generated by K, and then by the Thomason localization, if this was a theorem that's called a special case, right? If you take the compact generators, you take the log of the compact generators, you get the whole category.
So this is by the lemma. So this is by the lemma. But what I want to show is that I can remove this Z here. So if I take the smallest localizing subcategory containing K in the dx and then move Z also here, then I'll, oh, no, this here I don't need to remove. Let's.
Well, first of all, clearly we have an inclusion. If I take a localizing subcategory in the smaller subcategory dxz, so clearly this is contained in the localizing category d of x. Well, since we just simply use the larger category, the localizing closure could be larger. Right, so that's one inclusion. So then another inclusion is also quite simple. Well, if you take this localizing subcategory generated by K, so clearly this is in the d of x sub z, right? This last inclusion is because d of x sub z is localizing. Right? If you have this property for the family of objects, then this will be true for the coproduct of these objects. So then this localizing, so we have these two trivial inclusions, and we know that the beginning is the same as the end. So finally, the conclusion from this is that if we take the localizing closure in the derived category d of x in the Koszul complex, we will get the complexes with homogeneous apportability. Okay, so from this, another simple observation is that if I take some object Q, which is perfect on the open complement U, and so this is, since we know that for any quasi-compact, quasi-separated scheme, this U is clearly quasi-compact, quasi-separated, so this U is contained in the compact objects of the DU. So, say, if Q is like this, then there is some P, which is a compact object, in the d of x, and since this affine situation, know that this coincides with the perfect objects on x, such that if I take Q plus Q shifted by 1, this is isomorphic to the P restricted to U. That was the last theorem of Thomason localization that we showed for the compact objects, and there was some kind of improvement of that theorem by using K0, that actually the complement that you can take is just the shift of this object. So this is where we used that improvement in algebraic geometry. Okay.
Here x is affine, right?
X is affine, yes. And this actually finishes the affine situation. And now let's do some non-affine stuff. So the lemma, next lemma.
From which point we assume that x is affine?
From the start.
Yeah, from the beginning, when I start discussing Koszul complexes, for example, I use it here.
Yeah.
yeah, we consider v equal to spec of r, and then we change v to x.
Yeah,
It's just
so-
the
so-
same.
I think I just wrote this 2 pages, maybe with some, or one page in 1 week, with another page in another week, and I changed notation. So this x that I have in this computation is still the spec of some ring R.
Okay, so in the
Can you
following,
please repeat last step? Why does this P exist?
Hmm?
Why does this P exist?
by the Thomas localization. Well, if remember that
If we have such a quotient, so that's a category with the nice properties, namely this is log of some compact object, right? And in this case, we show that if you kind of restrict this functor from this category to this category, to the subcategory of compact objects, then for any compact,
well, then this functor is what's called dense, right? So the thick of the image is everything. And then we improve this by using K0, that the complement that you can take is actually the shift of the original object.
Mhm.
So this exists by the Thomas localization at the very end of that chapter where we discuss K0. Okay, so let me in the next lemma assume that I have X being a union of two open subsets, so union of U and W. So where U is quasi-compact open subset and W is affine open. This is kind of like an induction step for the constructing of X. I constructed U on the previous step and then in blue additionally one open piece, or one open affine piece. So then the functor, which is just the restriction of the shift to the U. So write it like that. Well, actually maybe there is a much better way to just write this as the J upper star. So the restriction to the U. So that's the functor from the curve of X to the curve of U. Right? If you restrict perfect complex to an open subset, you still get the perfect complex. So this functor is dense.
What is this?
Meaning that the thick closure of the image of this functor is everything.
So maybe I need to write this.
Thick of the J upper star of the perf of X. This coincides with the perf of U.
Okay. So proof. So I'll prove this and then we'll take a break. Okay, so take an object Q, which is the perfect over U. So by affine case, there is PW, which is perf on the W, such that PW restricted to the intersection of the U and W. This is the same thing as the same thing meaning the quasi-isomorphic, since we work with derived categories. So this is the same thing as the Q plus Q shifted by 1, and then restricted to the intersection.
So for the affine case, I just used this discussion before the lemma. Okay?
So we kind of consider U intersection with W and yes, we okay.
Yeah. So we have this kind of on the U, right? So U intersect with W on some open subset, and then there is this complement in the W, which is what before we called Z.
So do we know that Yes, so we know that if we have some perfect complex on U intersection with W, then there is such PW.
Yeah, because that would be an open subset in the affine subset, and that's this statement.
Yeah. So we know that any perfect object of U intersection with W is comes from perfect objects of U.
So here I'm saying that this is perfect object on the W.
Yes, but you so the affine case is working when we take perfect objects of U intersection with W. There we take perfect objects on U.
Yeah, so the
So you
Oh.
take perfect objects on U, consider perfect objects of U intersection with V, that Q restricted to U intersection V, and then take PW. Okay.
yeah, I would explain it like this. So I have this affine situation as before, but now the affine scheme is W, and inside this affine scheme, what was before I called U, now this is intersection of the U and W. And then for this open subset of the W, you just use this statement. But I think this is more or less the same as what you said. Okay, so we have this PW that lives on the affine piece W, and then I just said by definition over W we have P, which is perfect over U, and they coincide on the intersections. So P here and PU restricted to the U intersect this W coincide with the PW restricted to the intersection. Right? So then we can glue them together. We can glue PU and PW to some object P, which will be a perfect object on the X. Right? Because the being perfect, I can check locally, and locally on U and W everything works. So this is perfect, and that's what we need, right? Because this P will satisfy the property that we want. That will be, if we take this P and restrict this to the U, we will get the object that we start with this U.
Yep.
Well, up to direct sums, of course. Okay, so let's take a break. 10 minutes break.
Томасом localization. А что такое Томасом localization?
Просто компактный, рожденная, факторизуется почему-то
То есть это серия утверждений вот про...
Да, обычно локализация Томаса, это то, что как бы у меня было естественным образом определенное некоторое количество утверждений, но это просто ситуация про то, что вот у вас есть компактная порожденная категория, в ней выбираете набор компактных объектов, берете лог от этого набора компактных объектов, соответственно, факторизуете по этому логу, получаете, метод назывался там категория S, R и T.
Да.
И там была потом серия утверждений, что верно. Например, там, первое, что мы доказали, что там есть как бы правый сопряженный, то есть что локализация Томасона является локализацией Босфилда. Вот. Потом мы доказываем всякие утверждения, что, например, что такое там компактные объекты в R, да, это оказалось, что это thick от образующих. Потом мы доказывали, что этот функтор там сохраняет компактность. Потом мы доказывали, что функтор на компактных fully faithful.
Да.
Вот всякие такие вещи. Вот в совокупности все эти утверждения, они называются теоремой локализации Томаса.
Вот как получается, вот что Q плюс Q сдвинуто на 1 и замолвка по ограниченному налу? То есть мы доказали, что...
Это самое последнее утверждение из локализации Томаса, но помните, потом я сказал, что давайте это... Там было утверждение, что просто какая-то там категория компактных объектов, она плотная там, другой категории компактных объектов, помните? Но тут только вот началась теория, последнее утверждение.
Да, там последнее утверждение было про то, что если взять, применить жизнь со звездочкой сверху как компактным вес и взять толстую оболочку, то получится компактная
Да.
в каком-то тау.
Да. Но так что означает, что только вот взять плотную оболочку? Это означает, что с точностью до прямого слагаемого
Да.
вы получаете как раз такой объект, что вот найдется такой объект, да, ну, например, в этом утверждении, что найдется такой объект здесь, да, компактный, что как бы если вы его
ограничите, то у вас получится объект с точностью до прямого слагаемого.
Да, ну неизвестно какого.
Да. А потом мы использовали канон, чтобы сказать, что прямое слагаемое можно выбрать в виде просто сдвига, потому что там просто нужно было, чтобы он как бы реализовался в этой категории. Чтобы он реализовался в этой категории, если у нас плотная категория, единственное препятствие было это его класс в каноне. А здесь класс К0, конечно, попадает в К0 под категории, потому что класс в К0 вот этой суммы это просто 0. Поэтому он находится в К0 от категории, значит этот объект на самом деле под категории. То есть такое ограниченное время.
И тут прям важно, что это не абы какой прямой слагаемый, а модуль. Иначе мы спереди смотрим.
Да.
А вот разные факты про то, что жизнь со звездочкой сверху и push-forward, и тензорное произведение коммутируют с произведениями. Это мы из них доказывали какие-то?
Ну, для жизни верхней звездочки это очевидно.
Это потому что тензорное произведение.
Ну, потому что это самый право сопряженный функция. G с нижней звездочкой.
Да.
Поэтому для тензорного произведения это очевидно. Для push-forward, для квазикомпактных, квазиотливых морфизмов мы это доказывали.
Да.
Ну, почти доказывали, я в какой-то момент свел все к пучкам и сказал, что для пучков вы должны это знать.
А то, что тензорное произведение коммутируется с произведениями, это...
С произведениями?
Да.
То же самое по сопряженности.
Из-за того, что он левый сопряженный,
Да.
как холм.
Левый сопряженный сохраняет его пределы. Сейчас,
Да.
сейчас.
Да.
Сейчас, что-то не то. Да. Это самый pullback, это левый сопряженный.
Да.
Левый сопряженный сохраняет его пределы, да. Да. А для оценки для push-forward нужен какой-то аргумент, почему он сохраняет его произведение. Это не автоматически не следует.
Можно вопрос? Вы же короткое физическое получали?
Да.
Вот, я просто туда подался. Вы можете рассказать, как вы вообще с логикалистикой?
Мне кажется, что там очень много чего изменилось с тех пор. Там они постоянно нанимают людей, какие-то люди не приходят. Когда я там учился, там прям чисто геометрической геометрии было не очень много. Там было много классик, который скорее занимался производными категориями, но не то, чтобы напрямую только алгебраической геометрии интересовали. Особенности интересовали, представления с этим алгеброй интересовали. Но везде с точки зрения как производных категорий более-менее все. Бухлайс, но он в 2017 году. Поэтому с ним не сможете пересечься. Да, и там в какой-то момент были, там Стивен Павлов был, он занимался всегда такой очень сложной, очень продвинутой арифметической геометрией. Я думаю, что он все еще там, ему лет уже довольно много. Джейкоба Циммермана они тоже недавно наняли, он всегда интересовался пересечением аналитической теории чисел и алгебраической геометрии. Он очень как бы интересный человек, достаточно сильный. Но он был там, работал как раз последний там, год, наверное, когда я там был. Я слушал его курс планетарной космологии, но я, честно говоря, уже занялся диссертацией, ну, то, что было времени, что там продумывал детали. Вот. Кто там еще по алгебраической геометрии, я прям даже затрудняюсь сказать. Но такой, как бы, настоящий, какой-то алгебраической геометрии.
Нет, ну что-то рядом. Ну что-то рядом. Ну, мне, например, еще советовал Марко Галтьери.
Марко Галтьери это, конечно, комплексная геометрия.
Ну, тоже хорошо.
Да, Марко Галтьери это как хороший вариант. Если вы более геометрические вещи хотите, это хороший вариант научного руководителя, потому что, ну, он, с одной стороны, очень требовательный, но с другой стороны, очень как бы помогающий, там, в смысле, вот, найти там постдок, потом он будет помогать, возможно, там, ну, как бы не оставит вас и после этого, то есть, возможно, будете совместно писать работу всю жизнь, если будет вас научно руководитель, если, разумеется, все будет хорошо. То есть он, с одной стороны, требовательный, с другой стороны, такой, как бы, опекающий. Вот. Ну, и у меня еще был, как бы, вариант, который я рассматривал, это был Джоэл Каплицер, тоже вполне себе выдающийся математик, но он, конечно, скорее работает в области теории представлений. Алгебраическая геометрия Но английскую геометрию, разумеется, знает. Вот в какой-то момент, когда у нас был курс английской геометрии, я читал Сережу Архипов. Он там заболел чуть ли не на месяц, он его заменял, и довольно интересно и хорошо рассказывал.
Как фамилия?
Джоэл Камницер. По-моему, так, но я не уверен. Может, это на сайте. Потому что вы поймете, что у него работы всякие, принципы теории представления. Ну, такой продвинутый теория представления. Весьма полезный. Вот. Я не знаю, как он как научный руководитель, но он точно очень хороший математик, у него точно какие-то безумно конечно интересные задачи. На самой развитой этой области теории представления. Возможно, у него там есть какая-то геометрическая теория представления, где появится логарифмическая геометрия. Вполне как бы естественно была ситуация.
Ну, по теории представления вроде Браверман.
Браверман, да, ну когда я там был, там не было, короче.
А что вообще в плане вот, общей активности математической жизни? Я все-таки говорил, что там немножко скучные студенты местные. Немножко глупые. Но я как бы, может, еще глупее, так что ничего страшного.
Ну, честно, кстати сказать, когда я учился, вот у моего научного руководителя был как раз такой цельный расцвет, ренессанс, то есть в какой-то момент он ни в чем не участвовал, но они типа открыли новый кампус где-то там за городом, и он там был деканом, и он типа там занимался строительством, он был сильно до этого. А потом вот как раз когда ему было 60, у него была огромная группа, то есть это было типа там 7 аспирантов, 4 постдока. И, соответственно, был семинар у нас собственный, ну, для всех этих людей, которым там приглашены среди докладчиков, и потом мы там шли на ланч, и там была проблема, что типа, надо найти еще аспирант, чтобы всех вместе нас можно было посадить. Вот. И вот вокруг него была постоянно какая-то деятельность, то есть там были студенты, ну, посильнее, были послабее, но там, в общем, были посильнее. И, в общем, правда, сильный человек, которого я там знаю, он был в Великобритании. Он закончил Warwick в бакалавриате, на PhD приехал в Торонто. Прям местные какие-то ультрасильные, не могу такого сказать. Но в основном русских там было достаточное количество, русских, украинцев. Вот я в этой компании крутился, плюс компания по научному руководителю. Ну и там был местный человек, которому было интересно. Да. Ну там, кстати, русские еще довольно часто идут к Хованскому. Тоже, кстати, геометрическая геометрия. И вокруг Хованского тоже были какие-то интересные люди. Ну, правда, они русские были. Ну, в общем, я не знаю, как это оценить, как насколько там. Там единственное, что я могу сказать по поводу организации процесса, что у них там 12-недельные семестры. То есть, например, там к маю уже все заканчивается, в мае уже занятия нет. И это, например, означает, что если вам читать какой-то сложный курс, то там просто ничего нельзя успеть. 12 недель, ну там 3 лекции по 50 минут, стандартная схема. Ну, Марко Галтьери как нам рассказывал геометрическую теорию вариантов. Ну и там натурально 6 недель у него было проверительные сведения, и только 6 недель мы геометрическую теорию вариантов позанимались. Это просто было одно из моих таких ярких впечатлений. Надо было отзывы писать, я правда написал, что типа, курс на 6 недель на самом деле. То есть там, ну, как бы вот в плане того, что вы там будете, да, что-то послушаете и научитесь, ну, скорее всего, не получится, потому что просто человек начинает что-то рассказывать и ничего не успевает. Вот у нас был курс алгебраической геометрии, типа 12 недель, из которых там Сережа Архипов 4 лекции провалил, ну, это никакое. Ну, как развлечение забавное, но что-то выучить ничего невозможно. Вот. А с точки зрения семинаров, ну, в моем время, кажется, много людей приезжало и на наши семинары, и не только на наши семинары, в общем, была какая-то активность.
Понятно, спасибо.
Okay. So let's continue.
From this lemma, I want to derive a simple proposition. So proposition which will be more or less by the induction. So let X be a quasi-compact, quasi-separated scheme. Scheme U inside X is quasi-compact open subscheme. We take Q to be perfect on U. So then there is P perfect on the X such that Q plus Q shifted by 1 is quasi-isomorphic to the P restricted to the U. So the proof, since X is quasi-compact, I can write this as the finite union of affine opens, UI. So maybe call this N. Right? And then I have the following sequence of functors. Right? So from the perf of X, I can restrict this to the perf where I take a union of two things. So I take a union of the UI where I is running between 1 to the R, union with the given U. And then I continue doing this. And in the first step I dropped, this is U to the N minus 1. So this is the union by everything except the last one. Right, so this X is obtained from this union by just gluing one affine, which is UN. So here, I already know by the previous lemma that I have a dense functor. Right? So that's a dense functor where W is, in this case, is UN, and the U is just this union. And then I just continue doing the same procedure. On each step, I'm going to drop one of the U's. So this will be some step. This will be the perf U1 union with U. And finally, the last step will be just the perf of the U. So each of these functors is dense, right? So then the composition is dense. Is dense. As composition of dense functors. Right, and then I can say that I can use this argument with the K0. Right. So since I have a dense functor, argument with the K0 give me the result. So I don't know how to write this K0 argument. Gives the result. So the only point on this lemma is kind of do this in the right order, because you can take this bunch of inclusions and you can kind of leave this by the previous lemma on each step, but then it will be quite complicated because, well, on the first step you get 2 summons, on the second step you get 4 summons, etc. So that's problematic, but if you use it in this order, I think it's quite clear what's going on. Okay, so kind of you can lift, in this sense, perfect objects on the U to the perfect objects on the X. This will be important in the main theorem, which I'm going to prove right now. So theorem. So this is theorem of the Neeman, one law. So Vandenberg. So just 2 words about the history. So the Neeman first proved the statement that if you take quasi-compact quasi-separated scheme, then the derived category is compactly generated. So this was 1996, and then
6 years later, Mondel and Vandenberg improved this theorem and they proved the following.
So let X be a quasi-compact, quasi-separated scheme. So then the derived category is compactly generated by a single perfect complex.
So it's like in the affine case. In the affine case, you can take this simple perfect complex to be just a ring. In this case, there is just a claim that there is a single perfect. And since this is perfect, we know that it's necessarily compact. Okay. As usual, since this is quasi-compact, I can take a finite union of the n affine opens, and I'm going to fix notation, so U will be this union up to n minus 1, so except the last un, and the last un I'm going to call V. So of course the proof that I'm going to do is to prove by induction on n. So the proof
is by induction on n. So the base of the induction you already know.
So let me also fix some notation. I'm going to call Ju to be an open inclusion of the U into the X, and the JV also the open inclusion of the V into the X. So I know by the induction hypothesis, I can say that there is object Q in the D of U, since U is covered by the n minus 1 affine opens, such that, well, there is this Q. Oh, actually, I can even better write that this Q is in the perf of U, generating this whole category D of U. Okay, so I want to start with this Q and construct a new generator for the X. Okay, so first of all, by the previous proposition, I can say that there is some P prime which is in the perf of X, such that if I take this P prime and restrict it to the U, I'll get Q plus Q shifted by 1. That is by the previous proposition. So then I use that since X is quasi-separated, if I look at the intersection of the U and V, right, so these are also by the quasi-separateness, this is quasi-compact. So it is quasi-compact. Hence, I can write this intersection of the U and V as some finite union of the principal open affines. Right, since V is affine, I can do this. So I get myself a bunch of elements. So Fi are elements in the ring R, where I assume that the spec of R is V. And let me also, as before, use K as a shorter notation for the Koszul complex of this sequence of elements. Okay, so two observations about the Koszul complex. Well, first of all,
if I take the push forward along the map JV of the Koszul complex, so take this push forward and then restrict this back to the U. So what this will be?
So we take K in V and push it
Mhm.
in restrict V. Well, we can pull it on the intersection and no, it's not like this. Push pull. So yeah, we can kind of pull it on the intersection and push it on the U.
So what was the answer? Well, this is 0.
Why?
Well, the Koszul complex is the Koszul complex supported on the closed set defined by this Fis, right? And when you push it forward, it is still supported on the set. So it's restriction to the open complement, which is U, right? Is 0. So this. So I take this push forward of the Koszul complex restricted to the U, I'll get 0. And also I can take the same push forward of the Koszul complex and now restrict this to the V. So what I'll get in this case?
The same key K.
Yeah, this is just a general property. If you have any open embedding, if you kind of first restrict this and then push forward along the open embedding, you still get the same object. So the conclusion is that when you take this push forward along the JV of the Koszul complex, you get something perfect on the X, right? Because I can check this locally, and locally, well, X is covered by the U and V, and on U this is perfect, on V this is perfect. So that's a perfect object. And then I can introduce the generator. So I want to show that the generator is this object P. So P, this is by definition P prime, plus the push forward R JV on the Koszul complex. So I claim that this is P is a generator. Right, so this is perfect, of course, as the P prime by construction is perfect, push forward of the Koszul complex is perfect, so the sum is perfect. We only need to show this generates everything. Okay. So suppose that we have that the home in the derived category from the P shifted by n to the E is equal to 0 for any integer n. I want to show that this implies that the object E is isomorphic in the derived category to 0. Okay, so the observation here, since this whole home is 0, the home from the direct summons is also 0. So in particular, a special case would be, so 0 is equal to the home from the push forward along JV of the Koszul complex. Well, also need to keep the shift, some n, to the E. So this is also 0. But here I can use the adjunction and rewrite this as the home of the K shifted by n. And here this is just E restricted to the V. Okay, so all such homes in the affine situation, right, on the affine scheme V are equal to 0. So we can use this commutative algebra lemma and
Why they are equal to 0?
Hmm?
Why they're equal to 0?
Well, because this push forward of the Koszul complex is just a direct summand for the P, and for the P, all the forms are 0.
So then here restricted to V is equal to 0.
No, by the lemma, we can only conclude that the E restricted to V is quasi-isomorphic to the Rj lower star E restricted to the U and V. So here J is the inclusion of the intersection into the V. So this is what we get from the lemma. So then I want to show the following claim from which everything follows. So I claim that the map, the canonical map from the E to the R push forward along JU of the E restricted to the set U. Right, so this thing is an isomorphism. Okay, so to check that this map is an isomorphism, I can do this locally on the X. So we check this locally on the X. And so we need to check this for the U and for the V, right? So for open subset U, right? So we can take this canonical map, restrict the left-hand side and the right-hand side to the U. Oh, it follows again by the same argument that we used already here, right? When we compute the push forward of the Koszul complex restricted back to the V. So it follows by the identity that you have J upper star R J lower star. This is identity for any open inclusion. Right, so I restrict everything to the V. Okay, this restriction cancel this thing. What I'll get is E restricted to U is isomorphic to the E restricted to U. So on U this is clear. And for V, this follows by, let me call this formula star. So by what you already proved. Right, you just need to check that if you restrict the right hand side to the V, well, you get this thing, but this is kind of simple base change. Okay, so the claim is now proved. So we have this canonical map, which is an isomorphism. And now the rest is easy, right? Because when I have now home from the P prime of n to the E restricted to the U, sorry, no, this is not what I want. I want to take the P prime shifted by n, restrict this also to the U, and then can look at the home in the derived category of the D. Right, so if I look at this home, I can use the adjunction. So this restriction on the first argument, I can move it to the second argument using R J lower star. So this, sorry, not R J U. So this will be the home in the derived category of the X from the P prime shifted by n to the R J U lower star E restricted to the U. Right, so that's just by the adjunction. And this thing I can also, by this isomorphism, I can replace this by the home in the category D of X of the P prime shifted by n E. Right? Which is 0, right?
Yes.
Because again, I know this identity for the P, and the P prime is just a direct summand. So this home is 0. And this means that this home I started with is also 0. But when I take P prime, well, with the shift restricted to the U prime, I get Q plus Q shifted by 1. And Q was a generator for the D of U. Hence, if this home is 0, in particular home with the Q, so this implies that the home in the D of U from the Q to the E restricted to U is 0, and since the Q is a generator, E restricted to U is also quasi-isomorphic to 0. And finally, we have this formula.
Yes.
Right, so since E is isomorphic to this push forward, E restricted to the U, this is 0. So that's the proof. So indeed, this category is compactly generated by a single object. But you can see if you kind of, sometimes to do some computations, you need to know this generator and do some computation with this generator, and this is very not constructive. It's very hard to keep track of how you construct this generator.
Well, we can. Well, why it's just we take you don't understand how to take P prime.
Yeah, for example, we don't.
The P prime, that's the problem.
We only know the existence of the P prime. That's the problem. And but even if you know P prime, how are we going to explicitly compute this push forward for the Koszul complexes?
Yeah, but it's
Well, yeah, at least we can keep track of this push forward for the Koszul
yes, so
complexes.
it's, and we usually consider home from it, so it's
Yeah.
not so hard. This P prime is difficult.
Yeah, okay, so I'm going to raise the statement, and from this I want to derive two simple corollaries. So the first one is that if I keep the assumptions as before, if X is quasi-compact, quasi-separated scheme, quasi-compact, quasi-separated scheme, then if you look at the compact objects, you'll get exactly the perfect complexes. So we already have inclusion in one direction, so now I want to show that there is inclusion in the other direction, but actually the argument is a little bit different. I'm not going to use the inclusion. I just assume that the P is the class of all perfect complexes. So P be the class of all perfect complexes. Right? So we know that this, by first lemma, we know that this is every perfect complex is compact, so we have this inclusion. P is in the objects of the GX. And then we also, by the one of the results by the Thomason normalization, we can say that the log of P coincide with the D of X, because, well, definitely we can take this huge set P as a set of compact generators. And in this case, also there was a formula for the compact objects, and if you want compact objects, you need to take the thick closure of this. Well, yeah, so that's the problem. So let be, I can't take the class, but I can take the set of isomorphism classes. Yeah, so I need this to be a set. The class is not good enough. So let P be a set of isomorphism classes of perfect complexes. So then, by the Thomason localization, I can say that the compact objects here are the same as the thick of P, but the thick of P is clearly the same thing as the perf of X.
Do they form a set of isomorphism classes of perfect complexes?
Yes, yes.
Why?
You can check this kind of, you do this by induction, by how many
you check this for the ring, right? And then you use induction on the cover. Yeah, I think the statement is correct. Well, what I'm saying is that this category is locally small. And well, the category of modules is locally small, in particular perfect complexes. If you take isomorphism classes, this will be just a set, and then you do the induction algorithm. But of course, you can also simplify this. You don't really need this set, but you can take this set P to be just a set with a single object, which is just a compound generator. Right? And
Why thick B is perf X?
Well, it's clear, right? Because I'm confused how to explain this. It's kind of the logical observation. Well, if it's essentially the statement that if you just take this, when you take the thick closure, you take everything. The thick closure is at least triangulate category. Triangulate category is replete, right? So it closed under isomorphisms. So in this thick of P, you have all the perfect objects, right? And then you kind of add the direct summons, but the direct summons of perfect is already perfect. So it's, but for logical reasons, this is the same as the perfect.
Okay. Yeah, okay.
I can just another inclusion, so if you take some object from the sixth closure of P, why it lies in perfect complexes?
If you take something from the thick closure of P?
Yes, why the compact object is perfect.
No, because what operations you could do? You could do the shifts, which is trivial, right? You can take a distinguished triangle with two vertices being in the P, and this means that they're perfect. So then the third vertex is also perfect, right? Or you can take a direct summand, but the direct summand of a perfect is again perfect.
Yes.
Okay. So this is first corollary, and the second one.
Yeah, wait. Why do we even take this P? Why we can't work with perfects? What is this P for? Why we just say the perf X is sits in d of X complex, that the localization of perf X is d of X, and d of X complex is thick P, is thick perfect. Why I need this P?
Well, I need this P to kind of show how I use Thomason localization. That's the whole point. In the Thomason localization, I need some set of complex generators.
Yeah, okay.
So, yeah, but if you don't want to take this huge set, right, you can as well take this set P to be just the set with the kind of take a single perfect generator and consider this set.
Yes,
it also works.
Yes.
Yeah, it also removes the problem that you need to take a set because it's clearly set is for one element.
Mm-hmm.
Yeah, and you can also see that in this case, every perfect object you can construct from the thick closure of one perfect object. Okay. So this is one simple observation, and another simple observation that I don't think it requires a proof is that if f from the x to the s is a quasi-compact, quasi-separated map of schemes. So then the derived push forward and nets the right adjoint. So right adjoint. Right adjoint F with the cross. And by construction, it acts from the derived category of S with quasi-categorical homology to the derived category of X with quasi-coherent cohomology. And as a simple remark, we can notice that whenever you have two compositions, so the composition of the two maps, F and G, then the standard property that we, for example, have for the pullbacks is also satisfied for the cross.
So from what we know that this map exists?
Well, because we know that in this case, so this functor is defined on the derived category
Of X, which is compactly generated, so the result follows from the Brown representability and the fact that the push forward commutes with the coproducts.
Okay.
Right? So the Brown representability tells us that you have a functor between two
triangulate categories. The first category, which functor is defined as compactly generated, the functor preserves coproducts, but this functor with the prototype, also again the corollary from the Brown's representability. Okay.
Is it the same functor which is usually denoted, sometimes denoted by F or upper Schritt?
No. Well, maybe since I'm almost out of time, so maybe I'll answer your question right now. What you want for the shrink is the following. If you have some scheme, right, then you can embed this. So this is J, and J is open. Right, so this kind of like a quantification. So suppose this was defined over S. So this is map F, right? So X to the S. So the theorem that I'm using is called Nagata quantification. And Nagata quantification tells us the following: that if you start with a reasonable map, and I think that the map is something like finite type and separated. And so this is F is finite type separated. And then you can find the factorization like this. There's an open embedding and the proper map. And you can see this kind of relative version of a quantification. So this Nagata quantification is not unique. So potentially it could be different ones. And then by definition, you say that the F for this F that we have here, upper shrink, is defined as follows. So you first take F bar with the cross, and then you use the J, it is just standard pullback. So that's the definition, the standard definition of the F upper shrink. So you can see that if
F is proper, then F upper shrink coincide with the F with the cross by the Nagata quantification, right? Because in this case you take J to be just the identity. Or another observation from the Nagata quantification is that if F is open inclusion, right? For the open inclusion, you can take X prime to be just S. So then F upper shrink is the F with a star. So you can see that this is defined for a little bit different class of maps, more restricted class of maps. But that includes, for example, open inclusions, and for open inclusions, the answer is quite different than the F with the cross. So the reason to define this is that the base change for this functor is much better. So in particular, this is kind of, it works, for example, for open. So the property that you have is that when you take F upper shrink applied to the F restricted to some open subset, you can as well restrict this, take F upper shrink restricted this to the U, apply this of anything square. So X, there is inclusion of the U, so then there is maybe a side Y, this is F, there is this pullback, this is V, and this is what they call FU, right? And then there is the base change. So I can do it like this. So I first restrict, so then this is FU upper shrink, right? Or I can do it like this. I can apply the F with the upper shrink, and then restrict this, so f in the upper shift applied to the f, and then restrict this to the v. So that would be the property that you can obtain for the functor f upper shift, and there are no requirements of what f is in this situation. So if you can define this functor, then you get this statement. So it's finite type separated, and actually you can you can prove the negative quantification in a little bit more general case, something like essentially finite type, but that's not important. The base change for the f cross is much more complicated, and it works not in such generality. It works for example, what's called quasi-proper maps.
Quasi what?
Proper.
Quasi-proper.
Yeah.
Yeah, we kind of have 40 minutes.
Yeah, so that's the problem. So what I actually was going to prove today is this base change for the quasi-proper maps, and it looks like this is not possible to do. So maybe for the rest of the lecture I just formulate some results, maybe without proofs, and this is kind of will be the plan what you need to learn about the Grothendieck duality if you continue to go in this direction.
So if the map is an open embedding, then f cross doesn't coincide with f upper sheet.
Yes, there's some different functor, yes. If I remember correctly, you can do this, for example, in the affine case, and this will be something like f cross will be something like the derived completion along this ideal, which is right. You have open embedding, you have the closed complement, which is defined by some ideal. So you have the derived completion, and I think this will be the for the open embedding J cross will be the completion in that ideal, something like this.
Isn't completion is exact functor?
No, completion is not left exact and it's not right exact.
So how you take derived of it? How you take?
You don't need exactness to take a derived functor. You only need this to say that the zeroth derived functor coincides with your functor.
Yeah, that's true.
And in this case, it doesn't work, but it's not a problem for taking left derived functor.
Okay.
Okay, so maybe since I mentioned this, I just briefly say something about the quasi-proper maps. So that's a class of maps that was defined by Lipman, and this is the class of maps for which naturally you have base change for the cross. So, and the definition is nice. So a map of schemes f from x to the s is called quasi-proper if it preserves pseudo-coherent complexes. Quite general definition, and examples of such maps would be something like this. So first you can take f to be proper and s Noetherian. And 2, f is proper, flat, and of finite presentation. Of course, flat is quite a restriction, right? Not all interesting maps are flat.
So it's like named quasi-proper, but it's not smaller than proper. It's not smaller conditions than proper.
No, well, quasi-coherent is not smaller than coherent. I think here.
Oh yeah, that's in the other, right? Yeah.
So here I think the good idea, the idea behind was that is purely a categorical definition. Well, you just can define the notion of pseudo-coherent, and then you can define notion of quasi-proper using this pseudo-coherence. And there is a very interesting theorem which is quite complicated,
Yeah, but there's something like any coherent model is quasi-coherent.
Uh-huh.
So
And
there is
then-
no.
And this is not well. This is correct if you work with Noetherian schemes, and usually in this course I'm trying to do everything with quasi-compact separated, but the Noetherian is quite standard assumption in algebraic geometry. It's not very restrictive. If you work with Noetherian schemes, then any proper is quasi-proper.
Okay.
Okay, so a theorem by Lipman and Neeman. So this is Lipman and Neeman criterion. So this theorem I wasn't going to prove anyway. It's really complicated. That requires some additional techniques, which is called the approximations in triangulated categories. And it says, so this is criterion of quasi-properness. It says the following. So let E in the derived category of X be a perfect generator, which we constructed by the theorem that I just proved. So this is a perfect generator. So then F is quasi-proper if and only if you take the push forward of the generator and you get something, I call this E. So you take the push forward of the generator and you get something pseudo-coherent on the S. So it's actually enough to check this only on one object on the generator. Of course, in one direction that's a trivial, because this is a perfect object and particular pseudo-coherent. In another direction is highly non-trivial. But from this, you can derive corollary is that the class of quasi-proper maps is closed under any Tor-independent base change. Okay. Let me formulate maybe a theorem that I was going to prove, but I definitely don't have enough time to prove it. It's quite technical. It requires several steps. The theorem says the following, and I think this is the most, again, probably the most general statement about the base change for the F upper cross. So in this theorem, I still consider the standard Cartesian square as before. Take the diagram as before. Yeah, and then the proof of this theorem, you need some lemmas that I was proving when I was proving the base change. So if I had maybe one more lecture, it would make much more sense in why I'm doing this. And that was also the reason why I introduced the pseudo-coherent, because later I was going to use the quasi-proper maps. But unfortunately, I don't have time to properly finish this. Well, anyway, so the theorem says that whenever I have this Cartesian square, and in this Cartesian square, so let F be quasi-proper, and we assume that U has finite Tor dimension. So then we have the following base change statement, which is the new statement, which is not related to the standard base change. It says the following: you kind of take the standard pullback along the, well, you first kind of pull back with the F cross, then take the standard pullback, or you can do this the other way around. You take the standard pullback along U, and then you pull back with the F prime with the cross. and that is true for any f in the D plus of the S.
Notice the assumption about the D plus, and you cannot drop this. I think there are counterexamples. If D is unbounded, then this is not even true if you use just open inclusion. Yeah, and I think the proof is most natural precisely for the quasi-proper, well, because it's, remember when I think we will prove some statements about the quasi-coherence or something in the first argument. This is pseudo-coherent, so this is used in the proof, but I'm going to skip this.
So it's not some base change, it's some just...
Well, this is called the base change for the f with the cross. It's just a name.
Okay.
Well, because it kind of looks a little bit like a base change.
Mm-hmm.
Yeah. So this is one thing that you need, and yeah, you can notice that this works only for quasi-proper. If you're only interested in the proper, you're probably interested only in the function f with the cross. But if you want a larger class of maps and you want to have this base change, well, you need, instead of the f with the cross, work with the function f upper shrik. Well, the problem with the f upper shrik, if I want to kind of properly work out the theory, first of all, I need to show that there is Nagat compactification, and then the hard theorem is to show that the definition doesn't depend on Nagat compactification. So potentially I can choose different Nagat compactifications and get different answers, and that's a kind of annoying theorem, which is a long annoying proof. Okay, so what I want to say, from this theorem you can derive a corollary. It says the following: let f from x to the s be quasi-proper map of schemes. Let's take E to be any object in the derived category of X, and let's take F to be in the D plus of the what? Just a second. Of the S. Yes. So then we have a natural isomorphism of the following kind. So we take push forward, we shall apply to the derived form of the x between E, F upper shrik of the F, and then this is quasi-isomorphic to the R local form R F push forward E. And F. Okay. And you can call this a Grothendieck duality for quasi-proper maps, right? Because what you have by the definition, if you forget about this local home, and then you don't need to take this push forward, then it will be just a duality, which you get by definition, since the f with the cross is upper adjoint, is the right adjoint function, right? And then you can shapify this kind of shapified version of that duality. And the idea of the proof is the following: well, since you know this kind of globally, and if you have canonically you get map like this. So if you want to show this isomorphism, right? This is two sheets on the S. You can do this locally. You take an affine open subset in the S. You embed this. Right, so consider for the proof, and the idea of the proof is the following: you have X, F, S. Then you take an open affine and do the base change, right? Since you know the base change, you can kind of reduce everything to the base change and prove the statement locally for any U, as this is an isomorphism, if this holds for any U. So that's the idea. Well, the proof is not very long, but I think if I do this, I won't have time to do anything else. So maybe
derived several statements without a proof. Okay, so next is so simple that we can prove this without writing anything. So theorem, which is much simpler. So let f from the x to the s to the, well, let's say this is s, be a map of schemes. Map of schemes. Well, suppose the right adjoint exists. So here I don't assume anything about this map, I just assume that the f with the cross exists. And also suppose that the f okay, I'm a little bit confused about this. Exists. Well, maybe I don't need this. Let's. So this exists. Yeah. So then there is a natural transformation of functors where you take the pullback along the f of some f, take a derived tensor product with the f cross applied to the f prime. There is a map here to the f with the cross applied to the tensor product of the f and f prime. So derived tensor product so there's natural transformation like this, so where f and f prime are in the derived category of the y, and I think I also need to assume, sorry, not ys, and I also need to assume that so there is natural transformation of functors, which is an isomorphism for quasi-compact, quasi-separated S, and also F in the perf of the S. So if the one of the objects is perfect. So let's see. Oh, well, maybe as a part of a simple proof, let's see why we have a map like this. So we have the co-unit of the adjunction R F lower star F upper cross on the F to F prime to the F prime. That's the co-unit of the adjunction. And then we have projection formula, right? So R F lower star, which is applied to the L F upper star F tensor product, derived tensor product with the F with the cross of the F prime. So by the projection formula, I can identify this with the F tensor product with the R F lower star F with the cross applied to the F prime. So then combining this,
This is the F prime.
yeah, combining this with this co-unit map, I'll get the map that I want, right? So I get the map from the F, then the product with the F prime. Right, so this is exactly the map that I want, because I can use the adjunction. I can take this F lower star and kind of move it here. I use the right adjoint, which is the F with the cross. So by the adjunction, we get the map that I have in this statement. So again, the map is canonical. And now I want to say that the fact that this is an isomorphism when F is perfect.
What is the isomorphism? Projection formula.
Yeah, so this is projection formula, yes. Yeah, so let's look why this is true for a perfect F, right? So for example, let's take F to be the structure sheaf. So then I don't do anything here, I just take the F with the cross, apply it to the F prime, right? And the same will be here if the F, so if the F is a structure sheaf, so then the result follows, right? Because then we'll get just the identity that the F cross or the F prime is equal to the F cross of the F prime. So maybe let's call this map phi. Phi. So implies that phi is an isomorphism for trivial reasons. Right? But then
Can you repeat how we from this map get map phi?
by the adjunction, right? We have this map. So this is in the first argument in the home, this is second argument in the home. By the adjunction, I get the map from here to the F, to the, take this functor, move it to the second argument in the home, which is the right adjoint, which is this functor.
Oh, of course.
Yeah, so for the structure sheaf, this is clear. And the standard argument that I kind of formulated as an exercise before, that then on the, so I have a natural transformation of functors, they coincide on the structure sheaf, as they coincide on the thick of the structure sheaf, which is the perfect.
So where we use quasi-proper quasi-separateness of S. To say that the thick closure of X is perfect.
I don't think that you need this condition to say this. Maybe I don't see where I use this. Maybe I don't need this. So
We need something for projection formula.
yeah, but for projection formula, do we need this S to be? What was the assumption for the projection formula? Well, for the projection formula, I think we need several conditions. Yeah, you're right. So here for the projection formula, we need something, and maybe there have been some missing conditions that I didn't formulate in the statement, right? Because in the projection formula, I think one of the things I was using is that the RF lower star commutes with coproducts, right, in the proof. And so maybe the right thing to say is the following. Not that the S is,
But actually, if F is perfect, then we.
if F is quasi-compact, quasi-separated, I want to say.
F sheaf.
No,
F.
For quasi-compact, quasi-separated F, the map.
Yeah, that's the one condition for derived projection formula. For derived projection formula, there's another condition that F is perfect. If F in this situation is
If
perfect.
one of the conditions in that theorem is satisfied, then projection formula works.
Yes, so for projection formula we only need F
Yes.
to be perfect, but if there is no projection formula, if
No, the projection formula works for without assumption that some argument is perfect.
So
it's not working if f is not
no, it works.
QCQS.
It works.
No, I'm assuming that f is QCQS, yes.
No, you're assuming it's when you say that it's isomorphism if QCQS.
Ah. Yeah, with this I agree. Where we were?
We can use. No. We don't need an isomorphism and projection formula. It is enough to have a map from the left to the right.
Yeah, that's also true. And the map we will also get canonically.
Yeah, we have map without any condition.
Yeah, but I think the map goes in the other direction.
Yes.
Isn't this a problem? Yeah. So, what I need, where this is this?
I suppose it should just say that.
Quasi-compact, quasi-separated.
No, I think in the beginning, let F be quasi-compact quasi-separated map of schemes.
Yeah.
And
So-
then F cross exists, and then this map exists, and then everything.
Yeah, okay. Quasi-compact, quasi-separated. And then we don't need this. Where? So, the statement is that the map phi is an isomorphism if f is in the perf.
Okay, and the argument for the last statement I was going to use it was the one that we used before, right? If you have two triangulate functors on the left and on the right, you have two triangulate functors. There's a category on which they coincide, right? So the structure shift is definitely in that category. So that category is thick, and then any perfect is also there.
Why is this category thick?
You already asked this question. So it's essentially the idea is you have natural transformation between additive functors, and you look at the component of the direct sum of objects. This is sum of natural transformations for first sum and the second sum. Okay, so that's the argument. And to do this by this trick that we learned before. So that's phi f. So in this case, suppose that f, let's assume that f prime is fixed, and you can have a canonical component of the natural transformation for the f. So is isomorphism for any f which is perfect, and we keep f.
We need S instead of X.
Hmm?
So it is F is a structure sheaf of S. Because it needs to lie in DS.
No, instead of structure shift, now I take some any object f.
No, in the upper line. So,
Here.
yes,
So if
Because we
if
take-
f is a structure shift,
of S.
of s, yes. 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 And this is also s. Right, so in this argument, so f prime is fixed. Okay. So in some cases, we can actually compute this. No, let me maybe formulate this as a corollary. The following. So f with the cross preserves for products if and only if we have the formula f with the cross computed on some f coincide with the standard pullback applied to this f, and then the tensor product in the derived sense, of course, of the x, all the f cross all the all s. So in the special case when the f with the cross preserves coproduct, you can reduce computing this function to just computing the f with the cross to the structure shift. right? And this is of course the case for any f which is in the derived category of this. Okay. Okay, let's see. In one direction, if I have this formula, right, so then clearly this preserves coproducts, right, because the functor f with a star preserves coproducts, and the tensor product preserves coproducts. Okay. So preserve coproducts. So in the other direction, when you have this additional property that the f with a star preserves coproducts, if you look at the subcategory of objects, again, say now f prime is fixed, right, and f prime is what?
Wax, I think. Wax.
Oh, it's confusing notation. Okay, I have this formula for f which is perfect, right? And that's something that I get because the subcategory on which this works was thick, right? But now with this additional assumption that f with the cross preserves coproducts, if I look at the same category where they coincide, this will be a localizing subcategory.
Yeah.
So since this is localizing, and the localizing category containing OS, this is just the derived category.
Yes.
And so then this will be for any object in the derived category, and but I want to take as an f prime just the structure shift to simplify the formula. Yeah.
So in this corollary, we still need that f is QCQS.
Yeah. So the same assumption under which we have this formula plus the additional assumption that this preserves coproducts. Okay, so let me just say that subcategory on which phi now f. So subcategory of such f's is isomorphism, is localizing now. Localizing. Well, we use that the d of s is compactly generated. So it's localizing this categories compactly generated. So phi f is an isomorphism for any f which is in the log of the curve of the s, which is the d of s. And for the f prime, we just take the structure shift. Okay, so under some assumptions, you can reduce the computation of the new function to the computation of the old one, which is just f with the upper star. And there are examples where you can actually do this explicitly. So let me look at the two examples.
Yeah, and by the way, also a remark about this situation. When you have the assumption that f upper star preserves coproducts, well, that's condition for the new functor that we haven't studied yet. But there was an exercise in, I think, in the assignment 4 that this right adjoint preserves coproduct if and only if left adjoint preserves the compactness, and compactness is perfectness. So the condition in terms of the map F is that the map push forward with the F preserve the perfect complexes. If you have this property, then you have such a formula. And for example, this is satisfied if the map is, say, proper and of finite flat dimension. So, just as a remark. If F is proper and of finite third dimension, so then in this case, Rf lower star of the perf of X is contained in the perf of the S, and in particular F with the cross preserves coproducts. So that would be an example of such map where this is satisfied. Well, for example, if this is proper and flat, then we have this property. Yeah, and I wanted to look at the two examples.
How get this? Why F lower star preserves compactness?
Well, that's an exercise. You can verify. That's an exercise in algebraic geometry. So this then is an exercise, and this follows by one of the problems in the assignment. Okay, so let me formulate this maybe as the theorem. So let X be a quasi-compact, quasi-separated scheme. Let's take a closed inclusion of Z into X, and suppose that this is a locally complete intersection. So closed immersion. So of some codimension n. So with the ideal sheaf I. So let me fix notation for the normal bundle. So remember that this is local home in the Z from the I upper star of the I modulo I squared home into the OZ, so the normal bundle. Normal bundle of Z. So then, for this special case, we have the formula for the I with the cross, for the local complete intersection closed immersion. There is an explicit formula, so I can write this. Well, using what we've done before, I can write the pullback of the F, and then I need to take the tensor product with the pullback of F with the cross applied to the structure sheaf, right? And I claim that in this case I can explicitly compute this. This will be the nth exterior power of the normal bundle, and I also need to shift this by the minus n. So of course what we essentially need to show is that the I with the upper cross of the structure sheaf is this thing. Because
you also need to understand why in this situation it's preserved products. E upper cross.
Well, that's not a hard statement to check. Well,
Since it's proper and is defined in the third dimension, it's obviously proper, but not finite.
well, it's local of finite third dimension, so it's might be enough. Yeah, you definitely need to check that the conditions of the previous theorem are satisfied. And actually, you can do this by computing. So you can remove this condition as local complete intersection. You try to understand this functor of the closed embedding, what it is doing, and there is an answer for this. We have an answer.
Yeah, and Z is also quasi-compact and quasi-separated, yes.
Hmm?
Z is also quasi-compact and quasi-separated.
Yes, but I think this follows automatically.
Yeah.
Yeah, that,
Mm.
yeah, so the thing is that you can actually work out, if you just have a closed embedding, not necessarily local complete intersection, you can work out the formula for the I with the upper cross. And this formula is just something for the home, but I can't find this in my notes. So this is something like the, you take just R home from the structure sheaf of the Z into the something. So, and then from this you can see that this commutes with the, this commutes with the co-products, because locally you can, the structure sheaf you can resolve this by the Koszul complex. Yeah, no, for this you probably need, for this, yeah, to show that this commutes with the co-products, you need the assumption this is LCI. No. It's very hard to explain what I have in mind if I don't write these exact rules. Yeah, I just wanted to say that the last step from this observation, there is a special case of this formula. So theorem. So all the maps as before, the scheme is all the maps as quasi-compact, quasi-separated. So, but now I have a very specific map. Initially, I have requirement that F is proper and smooth of relative dimension N. So then in this case, I claim that the F with the cross applied to the structure sheaf OS, this is quasi-isomorphic just to the omega n x over s shifted by the n. So, and then in particular, from this formula, I will get formula for the F with the cross applied to any complex of quasi-coherent shifts, or complex of OX models with quasi-coherent homology, and we will get isomorphism. Like this. So that's an explicit formula for a smooth, proper, yeah, and smooth implies in particular that this is flat.
I suppose we should write what is relative differential.
Hmm?
What is relative differential? Omega x over s.
Well, you have this long exactly, well, not long, there is exact sequence where you have differentials on the x, you pull back differentials on the s, you take the quotient.
Okay.
Again, but this is the standard algebraic geometry. Well, and maybe I can use another 5 minutes to give a proof of this, because the proof of this is really simple when you know all the kind of general techniques. And so, of course, I don't need to prove the second formula, I only need to prove the first one, right? And in this case, I look at the diagonal map from the x product of this x, right? So this is LCI of codimension n. And this of course n, I didn't specify this. This n is the dimension of the fiber. So dimension of the x over s.
You said that it's of relative dimension.
Where?
Inside.
Yeah.
Right.
Okay.
Product over S, right?
Yeah, product over s. So this is of LCI for dimension n. Right. So now we have the following simple computation from algebraic geometry. Well, of course, we know that normal bundle in this case is just the omega 1 x over s dual, right? So, and the omega 1 is conormal, and this is locally free of rank n. So it's essentially how the omega 1 is defined, by the way. So then the omega n, and also shifted by the n, if I take the dual to this, well, then I'll get, of course, the top exterior power of the normal, and with a shift by -1. And if you do the local computation, you can also check that this is the, well, not the local computation, but if you kind of look at the previous computation, this is what you get, right, in this case. For the closed LCI embedding, you have this identity for the functor with the cross. Okay, so now you take the standard diagram with two projections on the P1 and P2, and for this diagram we do the computation. Well, first of all, you can write the OX as the delta with the cross by 2 with the cross of the OX, right? Because you also have some the diagonal map somewhere here, right? But when you use the diagonal map and then say projection P2, you get the identity, right? And this is just the cross of the composition, which is the identity. Okay. Now for the closed LCI immersions, I use the previous result and write this as the pullback along the delta of the pi 2 with the cross of the OX, tensor product with the delta with the cross of the OX cross X. Okay, now formula for the pi 2 with the cross applied to the sheaf OX. This is of course the same as the pi 2 with the cross applied to the F upper star OS, right? So the pullback of the OS is just OX. And then for this, I can do the base change. So this will be pi 1 with the star, F with the cross applied to the OS. So this is the way in this computation we need to do the base change, and that's why the formula for the base change, which I unfortunately didn't prove, is so important. So combining these observations together, we'll get that the beginning OX can be written, if we plug in the one formula into another, as the pullback along the map delta of the pullback of the pi 1 with the star F cross OS, right? Then the product with this thing, with the delta cross, but I can compute this as I know as the omega x over s n shifted by n, and then take the dual. Okay, and finally notice that if I take the pullback along pi 1 and then take pullback along delta, I still get the identity, so this doesn't do anything. So really this is just F cross of the OS, then the product omega n x over s 2, right?
So, and that's the result. Because this is just a line bundle, so what I need to do is just take a tensor product with the inverse of this line bundle, and that's the answer for the F with the cross applied to the structure shift. So you can see to get this result, you need to know the base change. This is one abstract result, and you also need to know the general case of the LCI closed immersions, and the case of the LCI closed immersions is can be reduced to the local computations to the Koszul complexes.
How many different classes? What has happened?
Well, I noticed that this composition, so this is just a pullback for the identity map.
Yes.
So I can drop this.
Yes, and then we rewrite the dual.
Yeah, and then I get that the structure shift is the tensor product of these two things,
Yes.
but this is just a line bundle.
Yes.
So I can kind of move it back to here
Yes.
and get the dual, right, in the statement. I have the dual, so.
Yes. On the second
The
line.
up, the second to the up.
Uh-huh. Yes. Okay. So it's unfortunate that I wasn't able to prove the base change.
Какой base change?
Hmm?
What base change?
No, the base change that I used, for example, somewhere here.
Ah.
The base change of the boundary with the cross. Okay.
Как так получается, что вот здесь в геометрической геометрии, в такой лазарийском возникает функтор с крестиком, а вот в аналитической обстановке, в этальной, в D-модулях такое не встречается? Или это не изучают там, а он есть?
Нет, другие трансформеры там не изучают, оно не случается.
То есть тоже есть?
Да, конечно. Да. Нет, ну вот в D-модулях, в этальных, все это есть, и там оно гораздо лучше устроено даже.
Вот именно F с крестиком?
Именно с крестиком я не скажу, рассматривают там с крестиком отдельно, там рассматривают F с повторяющим.
Да, это я знаю, да. В 6 операций входит, а вот
Да.
F с крестиком, то есть там же должен существовать к F с нижней звездочки правой сопряженной. Или там его нету?
Нет, он несомненно есть, но логика это свойственно сверхе. Свойственно сверхе вы можете доказать и для
Но именно F с крестиком, то есть не к F с повторяющим,